This is your lecture unit, Periodic Trends, Unit 4A. This will cover the entire unit, and you need to make sure you take wonderful notes and have printed out the notes prior to starting this, and to fill them in and pause at any time that you need to have a little bit more time on a slide. So, why are periodic trends important to scientists and engineers? Well, the simple answer is material science. Scientists and engineers are always looking to create better materials or solve new problems. It can be argued that the largest advancements in the history of technology are due to materials. For example, iron and steel age, they led to the industrialization and higher buildings. Silicon, it drove the expansion of information age. And even aluminum has its spotlight in history. It's light and non-corrosive. It's 8% of the Earth's crust. It's the most abundant metal found on Earth. Yet, until 1850, it was worth 2 times as much as gold. In fact, Napoleon had his servants eat on gold silverware, while all the elite and the nobility ate on aluminum silverware utensils. Even the Wright brothers got in on the action. There, you can see them to the left. They built the first aluminum engine, which they ended up painting in black because they didn't want their competitors to see that they were using a lighter material, which therefore would make them go higher and faster. So what made aluminum so much more expensive than gold in 1850s? Well, it was because it was so hard to isolate aluminum by itself. So the refinement process was very expensive. So even though it was so abundant, most of the time aluminum was found bonded with oxygen and made in aluminum oxides. So there was a German scientist during World War I named Alfred Wilm. And Alfred Wilm came up with the age hardening process, where he realized if he could add pressure and temperature over time, he could add different alloys to metals and make them not only keep their durability, but make them stronger. So he decided to add copper to aluminum, about 4% of copper to aluminum. The reason he did this was copper was really good at conducting electricity and other valuable ways, other ways that metals are very important. Well, when he did this, he realized that the aluminum was 1.5 times thicker, so you're getting more material, but 2 times lighter. So with this knowledge, he was able to create, down here on the right, you could see the Junker 1, which was the very first all-metal aircraft. This aircraft is why we have the airplanes that we do today. Alfred Wilm's invention of the age-hardening process was also led to the Empire State Building, which is one of the very first buildings to have aluminum in its framework, and even in the Washington Monument, you'll find at the very top one of the largest at the time aluminum pyramids, like largest chunk of aluminum found. But as you see in the center, in World War II, this was the Liberty ship, the SS J.P. Gaines. It was outside Alaska. And scientists are also interested in periodic trends because they want to know how materials are going to perform over stress. So there's something called the tensile tile, or the tensile stress test, that scientists will look at and see what is the capability of its brittleness and how hard is it and what's the elasticity and how stiff and tough will this material be, especially when external pressures are added. So this was one faux pas that happened with this all-steel wartime ship. But also Napoleon in the War of 1812 went from 600,000 men down to 10,000 men, which is less than 2%, because he insisted on having their uniforms be closed with the tin buttons, which when tin gets in very cold Russia at the time, present-day Russia, where they became brittle and fell apart. And so all of his men were having to hold their musket and their uniforms together, and most of them froze to death. But periodic trends aren't all in the history books. If you see up here, Elon Musk, who is the creator of the Tesla, has been trying since 2016 to create the most powerful, largest spaceship to be taking people to Mars. So he needs something that is fast, something that's durable, and something that's large. This means he needs a bigger fuel tank that is lighter. So he is using a new technology, which is the synthesized carbon fiber reinforced cryogenic plastics. And so between that and also carbon nanotubes, scientists are creating things that are smaller and more efficient and are able to find ways to do things that we couldn't do in the past. Even graphene, which is the thinnest material known to man, is just like the lead in your pencil, like the graphite, or what the diamond is made out of. It's all made out of carbon, but it's a single layer. And British scientists, a few years ago, finally were able to separate it, and now we're able to use this technology. Ironically, they had to use Scotch tape in order to separate it in this British lab. And if you took a sheet of graphene and you held it between your thumbs, it would actually, if it was the size of a football field, would not bend. That's how strong and thin the material is. So this section can be found in section 6.3, the periodic trends, in your digital textbook. There's more information on the blog on how to access this information, but you'll find it on pages 187 to 196. So this information is a review from last unit. We know you had the father of the periodic table, Demetrio Mendeleev, ordered the elements by atomic weights, and he noticed the periodic repetition of all the elements which had the families. Well, this was in 1869. By 1913, Henry Moseley, a British scientist, discovered the isotopes of elements, which led to the protons being more of a better way of explaining the periodic table. So he came up with the idea of periodic law is better stated as when elements are arranged in order of increasing, and here's the blank, atomic number, elements with similar properties appear at regular intervals. So if you look at this graph up here, you have the atomic number as you go from left to right, and as you go up, the atomic radius is changing. So you know, like this right here would be hydrogen, helium, lithium, and then as we go down, we can see that the radius starts to change. And about every 8 elements, we see a grouping. And we'll look at more of this graphing activity in class to see how this data is so important. Fun fact about Henry Moseley, which is not a fun fact, but he volunteered to be in the World War I as a combat duty officer, and he was actually killed by a Turkish sniper. After this, scientists were prevented from enlisting in the military to help preserve our scientists. This is an overview of periodic trends and what we'll be looking at. We'll be comparing periods and groupings. And a little bit of review vocab is that ions are a positively or negatively charged atom or molecule due to the loss or gain of electrons. We'll be looking at some new vocab words, and the main idea is that trends among elements on the periodic table are basically going to be looking at their size and their ability to lose or attract electrons. So pull out your periodic table at the top of your notes and fill in all of these awesome numbers that are popping up, the blue, the red, and the green. Pause this video and fill them in. Hopefully you have paused the video and filled these in on your periodic table on your note sheet. So you need to memorize the charges at the top that are in blue. There's a rhyme to remember these. 1 plus 2 plus 3 plus skip, 3 minus 2 minus 1 minus zip. Zip because the noble gases have no charge. Again, 1 plus 2 plus 3 plus skip, 3 minus 2 minus 1 minus zip. The valence electrons are in red. You can find that by using the group number on the periodic table. The transition metals have 2 valence electrons, and we'll see in Unit 4b why that is because of the electron configuration, while their charges will vary. There's a few other facts you need to know. Silver, number 47, has a +1 charge. Zinc and cadmium have 2+. Notice there's 2 of them, so you can remember 2+. And aluminum has 3+. Number 13, group 3, 3+. So I like to remember it as a staircase, 3, 2, 1, 1, 2, 3. So as you're going up and down the staircase, you have silver as 1+, zinc and cadmium 2+, and aluminum as 3+. Your noble gases do not have a charge, and you need to make sure you know the main group's valence electrons and group numbers. The periods are the rows 1 through 7 listed here, but you'll notice in the parentheses the energy levels have changed. So the main group element stays the same, so this is row 1 all the way across, energy level 1. Here's energy level 2, row 2. Row 3, actually an energy level comes back down, and this is energy level 3 also, and then we come back up here. And we'll look at more again in Unit 4b why that is happening. So notice the transition metals, the energy level is 1 minus the row, where in the lanthanides it's -2, and the actinides is -2. We'll look at this again on another slide. Anions, or ions. Ions are an atom or a group of atoms that have a net positive or negative charge. Again, this is review, and so I'm just going to go through these quickly. Remember that cations have a T in the middle, so that's how you can remember they're positive. Anions are negative, so that's how you can remember that they're negative, because if an ant bit you, that's negative. Also, you can remember the acronym California, Ca. California is on the west coast, so the metals are on the left side of the periodic table and form cations, and the nonmetals are near the Atlantic Ocean and form anions. The cations are positively charged. They're formed by losing electrons. The metals form cations, the elements are to the left of the staircase, and when comparing to the respective atoms, so meaning when you have a sodium atom and it forms a cation, it's going to be smaller, where an anion is going to be larger than its atom. They form negatively charged atoms, or ions. They're formed by gaining electrons. Nonmetals form anions, and they're the elements to the right of the staircase. So here we see the anion definitely looks bigger and the cation looks smaller. So let's look in more detail of why that is occurring. So here we have our sodium and our chlorine atoms, and they're also drawn out here. If sodium loses one of those electrons, we're going to use our new vocab term. Instead of calling these orbitals or rings, we're going to call them energy levels. So if the sodium loses an electron, it's going to lose an energy level. And now this one only has 2 energy levels, as compared to chlorine that has 3 energy levels. And it gains 1, so it retains that. So the chlorine anion is larger than the chlorine atom to begin with, and the cation is smaller than the original atom. Valence electrons. So why are these ions gaining and losing electrons? Well, it's to gain stability, because they want to be just like the noble gases. The noble gases have a full outer shell, meaning that they are very stable. Valence electrons in the outermost shell is what we refer to as valence electrons. Valence electrons are gained, lost, or shared in order to achieve an octet. The octet rule simply states that atoms are going to, in the main group elements, tend to combine in such a way, meaning they're going to be giving, losing, or sharing electrons, to have 8 in its valence electrons, or valence shell, giving it the same electron configuration as a noble gas. Again, we'll look at more electron configuration and what that means in Unit 4B. There are 2 exceptions. Hydrogen and helium, they only need 2. So if you think back to the Bohr model only has 2 electrons on the first ring, and that's why they only need a duet, 2 valence electrons. So here you can see that duet right here, it only needs 2. So if you get rid of this second and third energy level, you only need 2 to fill up. So hydrogen and helium only need 2 in their outer valence shell. So using the Bohr model, we would refer to rings as energy levels. The row number is the period number. The period number can assist in knowing the principal, that's that blank, energy level. The row number can determine the principal energy level. The representative elements are going to be, the row number is going to be the same as the energy level. Whereas the transition metals, the row number -1 is the energy level, and the lanthanides and the actinides are going to be -2 on the energy levels. Again, those are the green numbers that I showed you in a previous slide. So 2 vocab words to know: monatomic ions and polyatomic ions. So that's what we've typically been working with as monatomic ions. So some examples are chlorine and magnesium. Chlorine is found in group 7. It has 7 valence electrons, so it's typically going to gain 1 more to have that full octet, that full outer valence shell, and so it's chlorine -1. Where magnesium is going to is going to give away 2 electrons, so it becomes positive. So magnesium is going to be 2+. So a monatomic ion is an atom with an overall charge consisting of 1 element. Polyatomic ions are a group of elements with an overall charge. Polyatomic ions act as one single unit. So I like to think of them as a family, and you never split up a family. In fact, if you have more than one of the polyatomic ions, you're going to use parentheses. So here we have phosphate, and it has a 3- charge overall. So this whole PO4 acts as 1 unit. And then over here, ammonium has a plus charge, meaning it's lost an electron, and all of these are bonded together. We'll look at this more in our later units of how these actually are bonded. So these common polyatomic ions are listed on the back of your periodic table, and they're given to you on tests or quizzes. So you do not need to memorize these. You only need to know how to use this chart. Notice that it is labeled by the charge overall, and it makes it easy to find them. So here we have diatomic molecules. A diatomic molecule is something that is found in nature as a pair. So for example, oxygen. Anytime you find it naturally in the environment, you're going to find O2. You're never going to find oxygen by itself. So the 7 elements found naturally as pair in elemental form are diatomic, di meaning 2. 2 atoms in the same element that are chemically, covalently bonded together. Just as when people get up to go to the bathroom from a restaurant, they typically go in pairs. So you can think of a diatomic element as a pair. Here, you need to memorize these 7 diatomic elements: hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. Notice they all have a 2 subscript written. They make a 7, ironically, on the periodic table, plus hydrogen. So you can see that's 7. That's how I like to memorize them, but you can also remember some mnemonic devices, Brinkelhoff, or I have no fear of brown clean dice. You can also find many other mnemonic devices if you simply Google mnemonic devices diatomic elements. Alright, so we're going to learn how to count atoms. If there's no numbers by the symbol of an element, you're going to assume 1. So there's an imaginary 1 in front here and an imaginary 1 here. So there's 1 sodium. Here we have magnesium oxide. There's an imaginary 1 in each of these 3 places that I'm pointing to. So there is 1 magnesium and 1 oxygen. A subscript is a number written at the lower right corner of the chemical symbol. If there is more than 1, then a number is used. Here we have the diatomic element, hydrogen. So we have 2 of those. That's what that 2 indicates. Here we have 2 lithiums. Here we have 1, which is an imaginary 1, so we have 1 oxygen. Also, you'll have to use some of your math skills. So just as you distribute in math, we're going to distribute to all those things that are outside to the inside of the parentheses. This 2, though, will not get distributed to the 3 of the magnesium. So we have 3 magnesiums to distribute. So we have 2 phosphorus, that's the P. And the O stands for oxygen. 4 times 2 is 8. So we have 8 oxygens. A coefficient is a number that is written in front of a chemical symbol or formula. It indicates the numbers of atoms or molecules of a substance. So for example, here this 3 means that we have 3 carbons. That's an element. Here we have a molecule or a compound. So we have 2 water molecules, or we have 2 times 2 is 4, so 4 hydrogens and 2 oxygens. Again, that imaginary 1. So you can see here the 2 is going to get distributed to the iron. So 2 times 2 is 4, so we have 4 irons. Iron is Fe. And then 2 times 3 is 6. We have 6 oxygen. Here's a great slide to pause and look at, subscript versus coefficients, and make sure that you understand what the difference is and what the similarities are between the 2. So let's practice counting atoms. I would like you to pause this video and try these on your own. I promise you, if you try them on your own, you're going to learn better than if you just hear the answer straight off. So, learning check, try this on your own. Great, I'm so glad you tried these on your own. Let's take a look and see how you did. Here we have 1 sodium, 1 carbon, and 3 oxygen. For number 2, we have 3 calciums. This 2 distributes, so we have 2 phosphorus. 2 times 4 is 8, 8 oxygen. Number 3, we have 2 potassiums, 1 chromium, and 4 oxygen. Number 4, we have a coefficient of 3. This 3 has to get distributed to both of those elements. So we have 3 bariums and 6 chlorines. Remember, 2 times 3. Here, number 5, we have a polyatomic family or ion. So we want to keep this together. In this case, we have 1 of those. But individually, we have 1 nitrogen, and then 4 plus 3 is 7 hydrogens, 2 carbons, and 2 oxygen. Number 6 is a little bit trickier because you have a coefficient, parentheses, and subscripts. This 4 has to get distributed to the aluminum, carbon, and oxygen, and this 3 has to get distributed to the oxygen and the carbon. So in this case, we have 8 aluminum, 3 times 4, so we have 12 carbons, and then 3 times 3 is 9, so 9 times 4 is 36. So we have 36 oxygens. Here we have lead nitrate. Here is our polyatomic. Notice that I said when you have more than one of the polyatomics, parentheses are used. So the 2 is placed here outside of it. Here we only had 1 ammonium polyatomic ion, so the parentheses were not used. 1 iron, 2 nitrogens, 6 oxygens. Number 8. We have 2 of these polyatomic ions, so we've got to distribute some numbers twice. So we have 2 times 2 is 4, so we have 4 nitrogens. 2 times 4 is 8. 8 times 2 is 16, so we have 16 hydrogens, 2 chromiums, and 7 oxygens. Now we're going to take a look at periodic trends. So the first thing to know is that measuring atomic radius, there's a certain definition that you need to know. Why couldn't scientists just measure the diameter of a single atom? Well, an atom doesn't have defined borders. Remember that cloud is a 90% probability region where we find them. So if we take 2 atoms that are similar and the exact same, then we can take the distance between the nuclei, which is that dense positive nucleus, and divide it in half to find the radius of the atom. So atomic radius is half the distance between 2 identical nuclei of an atom that are bonded. The distance from the nucleus to the outer electron shell. Yes, think valence electrons. But again, you can only find these if you have two identical atoms to measure them. We're going to see this trend that as you go on your periodic table, the radius decreases going across a row. So as we go from left to right, you're going to see that overall they're getting smaller. We'll notice there's some sort of change happening here. And then as they're going to increase as you go from top to bottom. So overall, our largest atom down here would be francium. So they're going to increase to the left and down. There's two ways to memorize these. You can memorize which ways the arrows are going. You can also use the clock method that we're going to talk about. When we're talking about atomic radius, we're mainly looking at the main groups when we're talking about these trends, because as you saw in this slide, it kind of varies with the transition metals. It tends to change. So the atomic radius generally increases as you move down a group, and the outermost tends to decrease. So why are atoms larger as you're going down a group? Well, atoms are larger because the higher the energy level. So as we go down, we notice that we have one energy level in row 1. So take a look at your periodic table. In row 2, you have 2 energy levels. Row 3, 3. So you can almost think of this like a snowman. You're getting larger and larger and larger. So as you go down the periodic table, you have more energy levels, or something we call the shielding effect. So you have more rows. Or better stated, it increases because the shielding effect, you have more of those energy levels or rings. It's a little bit trickier as you're going from left to right on the periodic table. Why is it getting smaller if your mass is increasing? Well, as you're adding more mass, you're adding more force. So we remember that a proton is equal to about 1 AMU, and a neutron is 1 AMU, where the valence electrons, or any electrons, are almost so tiny, they're 1/1840th AMU, so they're almost 0. So as you're going across the periodic table, you're adding more force to the center, to the positive nucleus. Therefore, kind of like in a tug-of-war, you've got more members pulling with more energy. It would be like having a tug-of-war against, I don't know, let's say, here we have 1 adult versus 1 child. Okay, we can kind of see there. But as we go on and we keep adding more adults and you keep adding more children, adults have a lot more strength to be able to pull them in closer. So the second law says that, Newton's second law says that force equals mass times acceleration. So more force, more mass means more force. So as you're going across the periodic table, you can think of it, the nucleus has more power to pull them in. So imagine my arms are out straight and I'm able to pull them in closer to my body. So let's just kind of review a few of these items and make sure you've got these in your notes. So why is it larger going down? Well, you have higher energy levels as you go down. It looks like a snowman. So you have more energy levels. So we have 1 energy level, 2, 3, 4, 5, 6, etc. And we call this the shielding effect. It's your core electrons are blocked between the valence shell and then the ones on the inside. So the ones on the inside are acting almost as a blanket, and we'll see that play a part later in some other trends. Why is it smaller to the right? Well, you have an increase in nuclear charge. So as you're adding more of those protons, the additional, without adding more of the shielding effect, you're pulling those electrons in tighter. So there's a general decrease in atomic radius from left to right, and there's a general increase in positive charge of the nucleus as you go from top to bottom, so we see the size increases. Valence electrons are not shielded from the increasing nuclear charge because no additional electrons come between the nucleus and the valence electrons as you go from left to right. So you can see there's many different charts to look at that are in here. You can also remember this is the 9:30 trend. So where you have the minutes on the 30 and the 9 on the 9, the hour hand. These hours are pointing in the direction of increasing direction. So as you go from right to left on the periodic table and as you go from top to bottom, you're going to see an increase in atomic radius. That's meaning our left corner, and if you take a look at your periodic table, you'll see Fr, which is francium, which is the heaviest, biggest atom, atomic radius. So let's practice. So looking at your periodic table, you have cobalt, Co, versus nickel, Ni. Well, cobalt is to the left of nickel, so it's going to have a larger atomic radius. So cobalt would be the answer. Now let's look at phosphorus and nitrogen. So find P on your periodic table and find nitrogen. You'll see that they are on top of each other. So nitrogen is on top and phosphorus on bottom. Since phosphorus has an additional energy level, it's going to be larger. So in this case, the answer is phosphorus. Potassium versus oxygen. Potassium is on the left side, K, and oxygen is all the way on the right. This does not seem very simple now. So we have to take a look and think about this. Well, oxygen is at the very top, all the way to the right, and has 2 shells of energy shells, where potassium has 4 shells. 1, 2, 3, 4. So even though it's farther to the left and it's farther down, potassium would be the definite winner here. So potassium would be the answer. List the following in order of increasing atomic radius. So we have fluorine, gallium, and carbon. So find fluorine, number 9. Gallium is number 31. And then you have carbon, which is number 6. So the one that is going to be the smallest is going to be fluorine. Then you're going to have carbon, and then gallium. Between fluorine and carbon, fluorine is going to have more protons, so it's going to grow closer, it's going to be pulled in tighter, and they have the same number of energy shells, as opposed to gallium, which has 2 more shells than nitrogen, carbon, and fluorine. Let's look at barium, iodine, and gold. So locate gold, Au, number 79 on your periodic table, and then you also have iodine, I, number 53, and barium way over to the left is going to be Ba, 56. So these are all look like, as we're looking across, they are almost all on the same row. So you have barium is on 1, 2, 3, 4, 5, 6. It's on the 6th row and has 6 energy levels, whereas gold has only 5, because remember you got a -1, so it's really kind of like up a row. And it's kind of going towards the middle of the periodic table. And then iodine. Iodine has 5 shells there. So an increasing atomic order will be iodine, gold, and then barium. Finally, in decreasing order, meaning let's have the largest go first, and then you'll have the smallest last. So aluminum, number 13, sulfur, number 16, and sodium, all the way to the left, number 11. So these are all in the same row, and we know as we go across that they get smaller. So in decreasing order, we would have the largest one first, so sodium, then aluminum, and then sulfur. So sodium, aluminum, and then sulfur. All right, ionic radius is very similar, but now we're talking about anions and cations. So a cation has a smaller radius than the atom, and the anion has a larger, and we've already talked about that earlier in the video. Here is a beautiful chart that you can study and help reinforce those ideas. So A or B, why are cations larger than their respective atoms? And why are cations larger and anions smaller than their respective atoms? Well, B is correct because cations are formed when electrons are lost. So when these are lost, the electron repulsion is going to be greater net nuclear attraction per electron. So the newly formed ion becomes more condensed version of its neutral atom. In other words, as it gives off one, it's going to have less energy shells. Where the anion is going to gain, and therefore it has more electron-electron repulsion, and so it's actually going to be larger, and it's going to have more of those electrons pulling away from the protons. So let's practice. Which one has the largest radius? A calcium atom or a calcium ion? Well, calcium is a metal. It's found on the left side of the periodic table. It has a 2+ charge, meaning that it lost 2 electrons. So the calcium ion is a cation, and that one is going to be smaller. So the answer would be calcium atom has a larger radius. Manganese atom or manganese ion? Manganese is Mn, number 25 on the periodic table, and it is a metal, so it's going to have a plus charge, meaning that the cation is going to be smaller. Therefore, the atom of manganese has a larger radius. Let's look at selenium and selenium ion. So the atom versus the ion. Selenium is a nonmetal. It is going to gain electrons. Therefore, selenium ion is going to be larger than the selenium atom. Finally, chlorine. Chlorine is going to gain an electron, and it's going to be larger because of that electron-electron repulsion. So the chlorine ion is larger than the chlorine atom. Ionization energy is the second trend to look at. The energy required to remove the first electron is called the first ionization energy. The first ionization energy increases left to right across the period. And it's going to decrease down because the atomic size increases and less energy is needed to remove an electron farther from the nucleus. This is a chart that we'll look at more in another lab, but you can see that periodic trend is observed. So as we go from left to right, it's going to increase, and as we go from bottom to top, it's going to increase. So here you can see as you remove an electron, the ionization energy to remove the second one is a lot greater, and the next one is a lot greater. Again, we're going to look at this more in class. So you can notice a trend as you're taking off those electrons. You know that you're getting actually into a smaller energy level. So as soon as all the electrons are gone on the valence shell, you lose a shell, and then they become harder to lose because they're closer to the nucleus and the shielding effect is decreased. So generally as you go down the periodic table, it decreases, and as you go left to right, it increases. So here's the part to put in your notes. Again, I'm just repeating this in several different ways so it helps people remember it. Ionization energy is the energy required to completely remove an electron from an atom or an ion. You can remember this as the 3 o'clock trend. It's going to increase from bottom to top, and it's going to increase from left to right. Again, ignore the noble gases. They do not become ions. They're already stable. So why opposite of atomic radius? Well, in small atoms, electrons are close to the nucleus, where the electron attraction is stronger. So why is there a small jump within each group? Well, every time you get rid of one of those electrons, now you have less electrons versus the protons, and you have more protons pulling those in closer, making it harder for those electrons to be given away. So the stable electron configuration doesn't want to lose an electron. Here are some ionization energies that you can check out. So this is how much energy it would take to take off one of those electrons. Again, if you remove one, then it's going to be even harder to get rid of the next one. Let's practice. Which of these has a larger ionization energy? Again, you can also refer back to the chart behind. So cobalt and nickel. So let's find cobalt is CO, so here it is, and nickel. They're next to each other. Okay, well as you go from left to right, we said that it increases. So in this case, nickel is going to have a higher ionization energy than cobalt. Here we have phosphorus and nitrogen. So let's find phosphorus and nitrogen. Phosphorus, nitrogen. If you didn't have these numbers, you could still figure it out because you know the trend is from top to bottom, it's going to decrease, remembering that 3 o'clock trend. So that means that which one of these is going to have a larger ionization energy? Well, that's going to be nitrogen. Potassium versus oxygen. So we have potassium and oxygen over here. Well, oxygen is higher up, and we know as you go top to bottom that it's going to lose energy, so potassium should be lower. And also, as you go towards the left, you're decreasing. So potassium would definitely have less ionization energy, causing it less energy to remove that electron, so it's easier for metals to give up electrons. That makes sense. So in this case, our answer would be oxygen. List the following in order of increasing ionization energies. So you have fluorine, gallium, and carbon. So fluorine, gallium, and carbon. Again, you can look at the numbers or you can memorize the trends. You won't be given the numbers on a test, so you need to remember the trends. So gallium is going to be the least, then we're going to have carbon, and then fluorine. So it's going to go fluorine, and then carbon, and then gallium. For barium, iodine, and gold, we have barium, iodine, and gold. So we know in increasing order, it's going to be barium is going to have the lowest because it's most metallic, then gold, and then iodine. Because as we go from left to right on the periodic table, the trend is going to increase for ionization energy, and top to bottom it decreases. This one, last one says, list the following in order of decreasing ionization energy. Aluminum, sulfur, and sodium. So aluminum, sulfur, and then sodium over here. Again, they're all in the same row. It decreases as you go from right to left, so it's going to go in decreasing order. You're going to have sulfur, aluminum, and then sodium. Electronegativity. It's greedy. It's how greedy is your element, and the most greedy element of all is fluorine. So it's a measure of the attraction of an atom for the electron in a chemical bond. It's the 3 o'clock trend that you can remember. It's going to increase from bottom to top and increase left to right. You're going to ignore noble gases because they don't attract ions. They're already stable. So again, fluorine is going to be the most electronegative. It's the one that wants the electron the most. It has that first shell filled, and it just needs one more. It has no shielding effect. There's no fat layers, as I call it, between the valence electrons and that inner core of where the protons are of the nucleus. So fluorine is the most electronegative element. As you can see on this chart, it's a 4. It's based on a number from 0 to 4, and these charts will be given to you on a test if I ask you to do any calculations, but you should know the trend. As you get away from fluorine, they become less electronegative, meaning that cesium is least likely to take an electron. One, it has 7 shells. So if you think about it, between the nucleus and the outer valence shell, you have 6 layers of the shielding effect, or fat layers. So you have interference between those valence electrons and the pull from the protons on the inside, where fluorine only has 2 and has that one tiny shell acting as interference. So fluorine is the greediest, the most electronegative, and cesium is going to be the least electronegative. Again, this is information that I just stated, but just so that you have it on the chart. So why does it increase as you move left to right? Well, you have more valence electrons, and you need to fill the outer shell. So there's greater need to fill the outer shell to become stable. It's easier to add electrons to it. So why do you decrease as you move down? Well, you have a larger electron cloud, so you have less pull by the positive nucleus. Again, as you're going from left to right on the periodic table, you're not increasing the shielding effect. So we're looking at the fact that we're adding protons and electrons. And so it's going to be easier for those protons to pull those electrons in. And so now they really want to pull one more electron to become stable, because all the elements want to be stable and be like the noble gases. And as you go down, you have the shielding effect. So therefore, there's more of that interference or the shielding effect, fat layer, that is allowing the nucleus not to be able to attract any more of those electrons. So when atoms gain electrons, they can become larger because the addition of electron increases electrostatic repulsion. This is the idea that we've already discussed, but I wanted to put it back on here to keep in mind as we're going through these and to have an idea of what electronegativity part plays in with atomic and ionic radius. So let's practice electronegativity. So cobalt or nickel. So find where fluorine is on the periodic table. It's up here at the left, if you can imagine a periodic table right here. And we're looking at cobalt or nickel. Well, nickel is closest to fluorine, so therefore nickel is going to be the largest or the most electronegative. Between phosphorus and nitrogen, the one that is closest to fluorine is nitrogen. So that is going to be the answer, nitrogen. Between potassium and oxygen, oxygen is closest to fluorine, so oxygen is the largest electronegativity. We're going to put these in increasing order of the smallest to the greatest electronegativity. So again, we have fluorine, gallium, and carbon. So fluorine is the most electronegative, so that's going to go last. And then gallium is going to be the least, so it's going to go gallium, carbon, fluorine. For barium, iodine, and gold, it's going to go, if you look where iodine, gold, and barium, they're all near the bottom of the periodic table. So we're going to go distance from fluorine, so it's going to go barium, gold, and then iodine. So we're going to list these in decreasing order. So we're going to start with the largest and go down to the smallest. So look at aluminum, sulfur, and sodium. Sodium is farthest from fluorine, so that one's going to be the smallest. So we're going to start with the largest, which is the one closest to fluorine, so sulfur. So it goes sulfur, aluminum, and then sodium. So periodic trends, the ionization energy and electronegativity have the same periodic trend, the 3 o'clock trend. The electrons of smaller atoms are closer to the nucleus, therefore they have a stronger attraction. It's harder to pull those electrons away from the atom. Larger atoms are going to have valence electrons that are farther away, so they have more of that shielding effect. So it's easier to lose those electrons. If you think of a shepherd with all of his sheep, if he's only looking after about 10 sheep, he can really keep those sheep close to him and protect them against the wolves. But if he has 100 sheep, the ones on the outside, kind of like penguins, it's easier for the ones on the outside to get taken by a predator. So you have more of the layers of fat, so you have farther away from the person that's trying to protect them or pull them in. So metal reactivity and metallic characteristics, it's the 930 trend. Metal reactivity and metallic characteristics increase as we move right to left, and metallic reactivity increases as we move from top to bottom. So where's the most reactive metal? It's francium. It's down at the bottom. It's super heavy, it's got lots of shielding effect, and it's the most reactive metal. And it's the most has the most metallic characteristic. So you'll be given an activity series, and you can actually use this to help determine which metal is more reactive or less reactive. So the one that is higher, the one that's stronger, is on top, right? Number 1 is on top. So number 1 up here is going to be the most reactive metal. And then all the way down the bottom, the least reactive. You'll be given this chart on a test. So your metallic characteristics, why do they decrease as you move to the right? Well, more valence electrons increase the nuclear charge, and it's harder to lose electrons. And something that is metallic can easily lose electrons. Why does it increase as you move down? It's that shielding effect. You got a larger cloud, so that nucleus has less pull. So as it's going to increase as you move down, because it's going to be easier to get rid of those electrons on the outside. So let's practice metallic characteristics. When you're looking at cobalt and nickel, you want to look at the one that is on the left. Is going to have the highest, most metallic characteristic. So cobalt is more metallic than nickel. Between phosphorus and nitrogen, we're going to look for the one that is lower on the periodic table. So therefore, phosphorus is more metallic than nitrogen, although we know they're both nonmetals. But we're talking about metallic characteristics. Potassium versus oxygen. Potassium is going to be the most metallic characteristic. Listing the following in increasing order: fluorine, gallium, and carbon. Gallium is going to be the most, so we're going to start with the smallest, which is going to be fluorine, then carbon, then gallium. For barium, iodine, and gold, iodine is going to be the least, so we're going to leave that one. That's what we're going to start with. So it's going to go iodine, gold, and then barium. And then finally, our decreasing metallic characteristics, we'll start with the largest. And in this case, we're looking at sodium, sulfur, and aluminum. Sodium is more metallic than aluminum, so it's going to go sodium, aluminum, and then sulfur is the least metallic. Hooray! You have reached the end, the periodic trends summary slide. So here you have all the trends and all the information you need to know. Or my favorite way to memorize these is to remember that ionization and electronegativity have similar trends, and atomic radius and metallic characteristics and reactivity have similar trends. So for atomic radius and metallic characteristics, as you go down the periodic table, they're going to increase, and as you go across the period, they're going to decrease. Where the opposite for ionization is true, as you're going down a group, it's going to decrease, and as you go across the period, it'll increase. I wish you luck, and I will see you in class. Have a great day.